Hi everyone, it's Mr. Glover here, just about to get our next set of notes underway. So the idea today is that we're kind of shifting gears. We're still working in probability, but we're not necessarily working with the counting principles. We're going to go through another sort of type of probability problem and how to go about solving that probability problem. So today we're talking about mutually exclusive events. Um, we're going to start by kind of defining what mutually exclusive events are. And then we're going to talk a little bit about different strategies for solving problems with them. So first of all, when we're calculating probabilities, we normally divide, oops, that's a highlighter, divide the number of favorable outcomes by the total number of outcomes. Um, and sometimes problems involve situations where multiple events can occur. For example, rolling a 3 or rolling a 7. In these problems, we need to consider whether both of the desired events have an impact on one another. So for example, think about something like whether you were rolling a 1 or a 2. Does rolling a 1 affect rolling a 2? Um, Compare that to a situation where um, you had to select 3 people. Is selecting one person going to impact selecting the next person? That's the kind of thing you have to start asking yourself, which leads us to what a mutually exclusive event is. So two events are considered to be mutually exclusive if they can't both occur. So if they cannot both occur at the same time. For example, drawing an ace or drawing a king. If you were to draw a Venn diagram for drawing an ace or drawing a king, you would have a circle for your aces, you'd have a circle for your kings. So let's say this is your aces, this is your kings. Well, there's 4 aces in the deck, there's 4 kings in the deck, but there's nothing that's both an ace and a king. So these are called disjoint sets. Drawing a king or heart. This one's a little different because drawing a king can impact whether you draw a heart or not, because there are kings that are hearts. So if we have a king and heart, well, we've got 13 hearts, we've got 4 kings, but there is a king that's a heart. So these ones cannot be considered mutually exclusive because there's no way, or there is a way to do both. Versus the ace and the king, you cannot do them both at the same time, so they're considered mutually exclusive. So basically, 2 events are mutually exclusive if you can't do them both, if one immediately makes the other not happen, or vice versa. So let's talk about probabilities and how to calculate these probabilities. If you have 2 events that are mutually exclusive, and you want to calculate the probability of one or the other happening, you have to add the probabilities of both. So the probability of A or B happening is given by the probability of A plus the probability of B. For example, the probability of drawing an ace or a king, well, that's the probability of an ace plus the probability of a king, because both of those could satisfy the requirements. All right, probability of A and B. If they're mutually exclusive, you can't do them both at the same time. That means the probability of both happening is 0. And that's the big idea. The probability of A and B has to be 0 for them to be mutually exclusive. If we're talking about non-mutually exclusive events, the probability of A or B is given by the formula that we talked about way back at the start of this chapter. Probability of A plus the probability of B minus the probability of A intersect B. And this is the formula we talked about way back even in combinatorics when we were discussing ands versus or situations. And is when you used combinatorics, or was when we used this formula. Now, this formula technically is the same for both the non-mutually exclusive and mutually exclusive. The difference is that the probability of both happening is 0. So this third term just disappears. It doesn't count when we're talking about mutually exclusive events. However, if they're non-mutually exclusive, this is actually a number and it has to be part of our formula. So really, there's only one equation. There's not two. So when solving for probability problems, we need to ask ourselves, are these events mutually exclusive in order to know how to calculate the probability? So let's go through a few examples. Let's talk about determining the probability of drawing an ace or a 2 from a deck of 52 cards. Most of these we're going to start with by drawing a Venn diagram. Some of them we won't, but that's a good starting point for a lot of these. So an ace or a 2, well, we draw the Venn diagram. Oh, I don't know why it decided to make it a weird octagon shape. So there's our Venn diagram. It's a little bit lopsided, that's fine. One of these will be aces, one of these will be 2s. Now, in a deck of 52 cards, there's 4 aces, there's 4 2s, but there are no aces that are also 2s. So there's actually nothing in the intersect. So because the intersect is empty, these are mutually exclusive events. So if we want to calculate the probability of ace or 2 is given by the probability of an ace plus the probability of a 2. Technically, we could subtract the intersect, but that's nothing. Probability of an ace is 4 out of 52, because there's 52 cards in the deck. Probability of a 2 is 4 over 52, which means the probability of both or one of those happening is 8 over 52. And that probability is approximately 15%, 15.4% probability. All right, let's talk about the probability of drawing a king, a 7, an 8, or a 9. Now, this one's not going to be as convenient to do the Venn diagram for, because we would have to draw a circle for each of these and have them all overlap, and it's going to get kind of confusing. So we've got to kind of think about this question and frame it before we go to actually start the problem. So we've got the win conditions here are drawing a king, 7, 8, or 9. So we've got to ask ourselves, can these be can both 2 of these 4 things happen at once? Are they mutually exclusive? There's no 8s that are 7s, there's no 9s that are 7s, there's no 9s, 8s, 7s that are kings. These are all separate events. So these are what you would call mutually exclusive. Oops. Okay, so now the probability of getting a king, 7, 8, or 9 is given by the probability of getting a king plus the probability of getting a 7 plus the probability of getting an 8 plus the probability of getting a 9. We're just adding each of the individual probabilities up because each one could get us the win. So there's 4 different things that could increase our chances. There's 4 kings in the deck. So there's 4 over 52 for the first probability. There's 7 or 4 7s in the deck. So 4 over 52 for our second probability. There's 4 8s, 4 over 52, and there's 4 9s. So each of these is equally likely. If we add them all up, we will get 16 over 52. That's our total probability, which leads to approximately a 30% chance, 30.8% likely. Determine the probability of drawing a diamond or a 3 from a deck. So now, this time they are not going to be mutually exclusive. And to show you, let's do a Venn diagram. So here's our Venn diagram. One of these is going to be for a diamond, one of these is going to be for a 3. So 3 or diamond. In the deck, there's 4 3s and there's 13 diamonds. However, the 3 of diamonds is both a 3 and a diamond. So there is actually one card that can be both. So because of this, these are non-mutually exclusive. They can both happen at once. So if we want to calculate our probability, Probability of getting a 3 or a diamond equals the probability of a 3 plus the probability of a diamond minus the probability of 3 intersect diamond. And the intersect is this part that's both. So there's 4 3s in the deck. So the probability of getting a 3 is 4 over 52. Plus there are 13 diamonds in the deck. So 13 over 52. And there's only one 3 of diamonds. So we subtract the 1 over 52 because otherwise we're double counting it. We're counting it as both a 3 and a diamond, and our total probability is going to be inflated because we're going to have one extra outcome than is actually going to satisfy the demand. So in this case, we've got 16 over 52, which again is 31%, 30.8%. All right, so let's take a little bit of a different approach here. Matt and Carter are playing a board game that involves rolling 2 dice. In order to advance to the next square, they need to roll doubles or a 7. So we're going to make an outcome table, and we're going to see how many outcomes actually fit this criteria. The outcome table is kind of like a multiplication table, except you're multiplying by dice instead of by numbers. And there's going to be 6 different options: 1, 2, 3, 4, 5, or 6. So let's set up our table. And on the top, there's going to be 6 options: 1, 2, 3, 4, 5, and 6. So we finished building our table. All right, now I think this will be good. We're going to zoom in a bit so we can see, and we're literally just going to write out the outcomes. We'll maybe use a different, well, we'll use the same color. We'll highlight the ones that we care about. So this is a 1 and a 1. This is a 1 and a 2. This is a 1 and a 3, 1 and 4, 1 and 5, 1 and 6. We're just going to keep going. 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6, 3 and 1, 3 and 2, 3 and 3, 3 and 4, 3 and 5, 3 and 6. 4 and 1, 4 and 2, 4 and 3, 4 and 4, 4 and 5, and 4 and 6. 5 and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, 5 and 6. And lastly, 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5, and 6 and 6. We probably should have put commas between them or a slash or something, but we're going to recognize that these are just dice rolls, okay? Now, I'm going to highlight all the ones that would satisfy the requirements. We have to roll doubles or a 7. So anything that's a double, I'm going to highlight. There's 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. Anything that adds to a 7, I'm also going to highlight. 6 plus 1 is 7. 5 plus 2 is 7. 4 plus 3 is 7. 3 plus 4 is 7. 2 plus 5, and 1 plus 6. So any of these highlighted outcomes is a favorable outcome, okay? And actually, I probably should have given these different colors. Maybe I'll attempt to change one to green. All right, so anything highlighted yellow is going to be doubles. Anything highlighted green is going to be a 7. So now we've got to go back to the probability calculations. What's the probability of getting doubles? Well, there's 1, 2, 3, 4, 5, 6 outcomes, and then there's 6 times 6, 36 possible rolls. So the probability of doubles equals 6 over 36, which is 16.7%. Likewise, probability of rolling 7s, there's 1, 2, 3, 4, 5, 6 ways to get 7. Probability of getting 7s is 6 over 36, which again is 16.7%. Determine the probability of advancing, so the probability of winning. Now, to solve this, we've got to first think, are these mutually exclusive events? Going to our table, there are no green and yellow options. They're either doubles or they're 7. 3 plus 3 is 6, 4 plus 4 is 8. Nothing plus itself is going to get us 7 because we don't have decimals. So because they can't both occur, these are mutually exclusive events. So the probability of advancing equals the probability of doubles plus the probability of 7s, because either one of those options will win it for us. Technically, we could subtract the intersect, but that's nothing, that's 0. So the probability of doubles is 6 over 36. The probability of 7s are 6 over 36, which means our probability of winning is 12 over 36, which is 1/3, or 33.3%. Now, we could have just added up our answers from the other question, but I want to get you in the habit of solving these problems by figuring out if they're mutually exclusive, setting up your equation, and then filling in what you know. Because these next couple questions that we do, they're really kind of strange and they seem kind of confusing, but we're really going through the same process, okay? Now, a student-led study at MPSS found 62% of people skip breakfast, 24% of people skip lunch, and 22% don't eat breakfast or lunch. Okay, now we're going to have to build ourselves a Venn diagram for this, and it's going to look a little bit different. Okay, so we're going to start by doing the normal Venn diagram that we've seen before. But in addition to the circles, I'm going to put a box around everything. And there's a reason for that. This box is going to be what we call the complement. The box are the things that don't fall into the Venn diagrams. Okay. This is kind of turned into an ugly picture, but that's fine. All right, so I'm going to call this set A, and A is going to be the people who skip breakfast, okay? This whole circle has to be 62%. Set B, so maybe label it, that's A, that's B. Set B are the people who skip lunch. That's this entire circle, okay? And then this intersect are the people who skip both breakfast and lunch, all right? Now set C, and I'm calling it C because it's the complement, is this outer set, all right? Set C is everybody that eats both breakfast and lunch. They don't skip breakfast, they don't skip lunch, and they don't skip both. They eat both, okay? So set C is 22%. So that means that this outer box is 22% of people, okay? Now, I know set A, and I know set B, and I know this intersect have to add up to 100%. So I can work backwards to figure out what this all has to equal, and then I can work to figure out what's in the intersection here. We basically are filling this in, starting, we're kind of filling it in backwards. Instead of filling it in first and calculating our probability, we're going to have to calculate things to fill in the Venn diagram. So question 1, are skipping breakfast and skipping lunch mutually exclusive? No, you can skip breakfast and you can skip lunch. You can skip breakfast and eat lunch. You can do anything you want. So they're not. There is going to be a portion of people that do skip both. So no, they are not mutually exclusive. All right. Now, determine the probability that a randomly selected student skips at least one of breakfast or lunch. All right, so if 22% eat everything, 22% eat both. That means that if we subtract that from 100, 100% minus 22% gives us 78%. 78% don't eat both. Which means that everything in our Venn diagram now has to add up to 78%. So in other words, the probability of that student skips at least one, probability of skip greater than or equal to 1 equals 78%. So people are apparently more likely to skip something in the morning. And this is fake information. This is not a real survey. Could get you to do a real survey though. So let's write out what we know. Determine the probability that a randomly selected student skips breakfast but not lunch. We know 24% skip breakfast. We know that, this 24% skip lunch, so 62% skip breakfast, 24% skip lunch. We don't know, so I'm going to call it X% skip both. And 78% skip greater than or equal to 1. All right. So going back to our diagram, this plus this plus this have to add up to 78%. I don't know exactly how many only skip breakfast, but I do know 62% have said they skip breakfast, but that includes the ones that also skip lunch. I don't know how many people only skip lunch, but I know that 24% skip lunch and some of them skip breakfast. So I've got to figure out what's this middle part here. So now I can build an equation for this. The probability of skipping at least one, and I might need a little more room here. Probability of skip greater than or equal to 1 equals the probability of people who skip breakfast plus the probability who skip lunch minus the probability that they skip both. All right. The probability that they skip both has to be subtracted because they're not mutually exclusive, and this is the intersection. Okay. So we're going to fill in our numbers. The probability that they skip more than one or 1 is 78%. All right. That equals the probability they skip breakfast, which is 62%, plus the probability that they skip lunch, which is 24%, minus this mystery probability, which I'm going to call X. You can call it whatever you want. I just don't want to write P skip both a bunch of times. So it's X. I'm then going to subtract my 62 and my 24. So 78% minus 62% minus 24% equals negative X. And I'm going to get negative 8% equals negative X. Or in other words, 8% equals X. What I just found is that 8% of people skip both breakfast and lunch. So I can now fill in my table. Go back up to the top. And I know that this number is 8% of people. Okay. So we're just about done. We kind of ran out of room here, but that's all right. Determine the probability that a randomly selected person skips breakfast but not lunch. Okay. Well, going back to our diagram. Oh, this isn't going to lock for me. The probability of breakfast but not lunch is just let me shade it in here. The probability of breakfast but not lunch is this part. The entire circle adds to 62. I know 8% of them skip both. So we've got to figure out how many skip only breakfast. And it's just this shaded part. Okay. So the probability of breakfast not lunch equals probability of breakfast minus the probability of both. Probability of breakfast was 62%, but I know 8% of people skip both, which means that only 54 exclusively skip breakfast. 54% skip breakfast only. Okay. And now go back to our diagram because I want this to, when I first started doing this stuff, I found that the context is the most important part. So 54% skip breakfast only. Well, I can go back up here now and I can fill this in. I know that this is 54% of people. And now I can do the same on this side if I wanted to. I know 24% of people skip lunch. Well, if 24% is this whole circle, I could subtract 8. And I know 16% skip only lunch. If I add these up, they should add to 100 because that's all of my population. The people who eat both, the people who skip breakfast, the people who skip lunch, and the people who skip both is everyone. So it should add to 100. But all we really needed was this number. So it's kind of a weird way of doing the problem. Build this Venn diagram first, use the Venn diagram to, or fill the Venn diagram in, solving for certain percentages that you need to know about. All right, one more question. This is a similar question. It's kind of weird. Car manufacturer keeps the database of all of its sales. Their database shows that 43% of customers have heated leather seats, 36% have a sunroof, 49% have neither. Determine the probability of the randomly selected car having both heated leather seats and a sunroof. So again, we're going to build our diagram first, and maybe we'll build 2. We'll see. I find that a lot of people, the place where things kind of get weird and confusing is that you want to just write 43% over here, but 43% is the whole circle, not just this outer part of the circle. Okay. So let's say that heated leather seats, heated leather will be over here, and sunroof will be over here. We also have to account for the people who don't have either. That's going to be the outer portion of the set. I don't know if I really like this notation, if I'm being completely honest. I've always thought of this outer portion as meaning the entire population, and this Venn diagram is a portion of it. So it's not the best way to represent it, but it works, and it is a visual representation. And then this is neither. So neither is 49%. All right, that tells me that whatever's in this diagram has to represent the rest of the 100%. 100% minus 49% gives us 51%. So I know that this whole Venn diagram has to add up to 51. Okay, that's the key here. So we can now build our equation. The probability of having heated leather, sunroof, or both, one or both, is equal to the probability of having leather plus the probability of having sunroof minus the probability of both. And the reason we're subtracting it, I'll say it again, is because we can't count it twice. It's already been counted in the leather and the sunroof people. Otherwise, you're not going to have these add up. So the probability of having leather is 43%. We know that. So 43%. The probability of having a sunroof is 36%. The probability of having both is what we're trying to find here. We'll call it X. And then the probability of having one or both is this entire Venn diagram, which is 51%. Okay. So now we just have to solve for X. Move 43 and 36 to the other side. 51% minus 43% minus 36% equals negative X. That means negative 28 equals negative X, or 28 equals X, which tells me that the probability of having one or both equals 28%. And so now I'm tempted to just fill out this entire diagram just to kind of explain to you where you can go from here. So I'm going to do that even though the question hasn't asked for that. So if we go and build the Venn diagram again, we'll pretend it's nice and centered. All right. Now I think I had this one as leather, I had this one as sunroof, and this one as neither. So now we know that neither is 49%. Right? We know that 28 is the intersect. And I know that the number of people with leather is 43. So if the people with leather, 28% of them also have a sunroof, well, then I know that this is 15% right here. 15 plus 28 gets me to 43. If I know that 36 have a sunroof, but 28 also have leather, well, then 36 minus 28 leaves me with 12% having the sunroof. And then if we go and we add all these up together, or wait, what am I doing? That's not 12, that's an 8. If we add all these up, they'll add to 100. So I used this to fill in the middle of the Venn diagram. Then I can go back and I can take the number with leather and subtract 28 to get the leather that don't have both. I can take the number that have sunroof and subtract what has both to find how many people have only a sunroof. And now I've got all my statistics laid out. This wasn't really necessary, but I think hopefully it'll help some of you understand what we're doing with the Venn diagram and why we're choosing to do certain calculations. Okay, that's where we're going to end things today. So I've got a few questions for you. I've got 1, 2, 3 to 6. Question 4 is kind of weird. Question 4, treat it like these kind of problems, and it should work out for you, but it's kind of confusing in the way that it's worded. So it's almost like ignoring the context is the more important part, but the context is kind of worded strangely. So when you get to that question, if you have questions on it, just send me an email, let me know, and I can explain. All right, so I'm going to end the chat here. Hopefully you all have a good rest of your day, and I will see you all in our meeting tomorrow. Okay, bye for now.